These are the FAQs for the third day of the review for the test of Chapter 7. And the first one that you're looking at up here is from page 553, number 12. It just says perform the indicated elementary row operation on the matrix. So for number 12, they're telling us to take 1 times row 1 and then add that to row 2. Now what that means is row 1 just gets left alone. And so does row 3. They didn't even mention row 3. But to get row 2, since that is the last row they're having us operate on, that is an indication that we are really changing row 2 with this. So now what we have to do is go back to what we know and say, all right, well, if I take 1 times row 1, I'm just going to get row 1. That's not changing row 1. But I have to add that to row 2, and I'm going to replace row 2 with that. So 2 plus 1 is 3, and negative 6 plus 2 is negative 4, and 4 plus negative 3 is 1. And that was all you had to do for that one. This is just understanding of basic row operations. Then, these that you had asked for from page 553, was it? I believe. Let me take a quick peek. These were all on another video, so I'm not going to redo all of those. Yeah, all of these from page 553 were on other videos. So 17, 20 are on the video for chapter review day 1, so go take a peek at that. And 18 and 19 are on the video for 7-3 day 1, so go take another look at that one. Then we have solve the system of equations by finding the reduced row echelon form for the augmented matrix. This is all going to be calculator here. So with 43, what we have to do is come up with that original augmented matrix, and that comes from our variables, our coefficients with the variables. And notice there are 4 variables here. Kind of use that last line of information to show you that. So for the first one, there's 1x, 1y, negative 3z, but there aren't any w's, so you need a 0 in there. And that has to come out to be a 1, and that kind of looks weird over there at the end. There we go. And then the second one. There is an x, there is a negative 1z, and so what we'd have to do is put a 0 in place here for the y. And then we have a negative 1y and a 2. And then the last one has a 2x, 1y, negative 4z, and a negative 1w, and that has to come out to 3. So what we would do now is plop this in the calculator and then get that reduced row echelon form. I'm going to go ahead and stop the video and get this in. I put the matrix in there, and that's all through second matrix, and then you go over to edit. And this first one is in matrix A, and you can see that I have the 1, 1, negative 3, 0, 1, etc. on there. So now it's back to the main screen, second quit, and second matrix. And now we want it to do the math, and it's RREF, which you could just scroll down to get or hit alpha B. And there's our reduced row echelon form, and then call up the name of the matrix, so second matrix 1. And there it is, 1, 0, negative 1, negative 1, 2, 0, 1, negative 2, 1, negative 1, and zeros all the way across the last row. And that is supposed to tell us that something here has infinitely many solutions. So we did our little RREF on this, and we have 1, 0, negative 1, negative 1, 2. Then we have 0, 1, negative 2, 1, negative 1, 0, 0, 0, 0, 0. So what we are supposed to see here is that we have 1 here for x, a 1 here in the position for y, but there isn't anything for z and w because those are all zeros. That means z and w are all real numbers. They're infinitely many. You know, infinitely many z and w's will work with this. So now what we have to do is write this as coordinates. And what we know is z and w can be anything. So the rest of this is figuring out how do you explain to somebody what x and y are in terms of those z's and w's. So if they do find out what z and w is, they'll be able to find them. So you go up to the top line and you see that that's 1x plus 0y minus 1z minus a w equals 2. Well, move the z and the w over. So x equals z plus w plus 2. That's the formula that somebody would need once they know what z and w are. Then you do the same thing, but for the y. There are 0 x's, 1 y, minus 2z plus 1w equals negative 1. So solve that for y. That will mean you're going to add 2z to both sides, subtract a w from both sides. So that is 2z minus w minus 1. And again, those formulas are all ready so that when somebody does figure out what they want to use for z and w, they can just go ahead and plug it into the formula. So we do the exact same thing for number 44, but just because somebody asked for it, I'm going to go ahead and do that one anyway. Give me a second here just to erase these real quick. It's almost exactly the same. So in 44, you could see each of these at least has an x, y, z, and w. So maybe that makes this a little bit nicer so that you can see them all. 1x, negative 1y, negative 1z, 2 w's, and a negative 3. 2x, negative 1y, negative 2z, 3 w's, and a negative 3. So we're just making an augmented matrix here using the coefficients. 1x minus 2y minus 1z plus 3w is negative 6. And now what we want to do, of course, is get that in the calculator and find our REF. Now I already punched this one in as matrix B on my graphing calculator. So this time it's going to be second matrix. Again, we want to get over to math, and then we need alpha B, our REF, and then we're going to tell it second matrix, use number 2 for the name of this matrix. And you can see that bottom row down there. Again, just zeros all the way across. So let's write that down and interpret those results. And that one was 1, 0, negative 1, 1, and 0. 0, 1, 0, negative 1, and 3. And then we had 0, 0, 0, 0, 0. So once again, our z's and w's, because those last rows, remember this is an indicator for x, this is an indicator for y, but zeros all the way through here tell us that z and w can be absolutely anything. There are infinitely many solutions. So again, z and w, all reals. So our 4-part coordinates for this include z and w, and then we go back and figure out how to write x and y in terms of those two. So for the first line of information, we would have x, 0 y's, negative 1z, plus 1w equals 0, and now we just need to solve for x. So that will be z minus w. Again, that way, once they know what z and w are, they can just plug them in and get the other solutions. And then the next line has 0x but 1y, and 0z's negative w equals 3. Solve that for y, and you have w plus 3. And that one's done. So those zeros all the way across the board are to indicate to us that we have infinitely many solutions. On the next page, it just said write the system of equations as a matrix equation, AX equals B, with A as the coefficient matrix of the system. So this is what we do if we intend on using inverse matrices to solve a system. We say, all right, our coefficients for the X's and the Y's would be 2, 5, 1, negative 2, but it's not just coefficients with this. They do have an x and a y. And if we were to do the matrix multiplication on those two, which we can, we have a 2 by 2 and a 2 by 1. So we'll get a 2 by 1 as a result. That would give us 2x plus 5y and x minus 2y. Now, those two together will come out to be negative 3 and 1. Again, because this is 2 by 2, and this is 2 by 1. The 2's on the inside match, which means we can do the multiplication, and the result will be a 2 by 1 matrix. So we just need to tell them A is our little 2, 5, 1, negative 2. X is our little x, y. And B is our negative 3, 1. They didn't even ask us to solve it. They just said, write it. There it is. There's the system of equations that we could use inverses for, but we have to keep in mind that matrix multiplication is not commutative, so we'd have to be careful with the order. Number 46 is the same thing. What we need to do is just pull the coefficients off of the x's and y's and z's. Slap an x, y, z matrix next to it so that when we were to complete that multiplication, it would give us 5x minus 7y plus z, etc. equals. So we're just setting this system up. A is, of course, 5, negative 7, and 1. 2, negative 3, and negative 1. 1, 1, 1, our nice little 3 by 3 matrix. And x is our x, y, z. And B is our 2, 3, negative 3 matrix. Next up, 31, 32, and 34. Let's see here. Oh, 31, this is already on another video too. If you needed 31, go to the video for 7.5, day 2. Already did that one. So go to video 7.5, day 2. I'm not going to waste anybody's time, mine or yours, going through that one again. Number 32, remember what we have to do here is graph all of the constraints so that we can find where our vertices are. And with those vertices, then we can figure out where our minimum and maximum are. So we want to pretend that this says x plus y equals 90 and find the zeros to graph this. And they will, of course, be 0, 90, and 90, 0. And then the next one that we have here, the 3x minus y, is greater than or equal to 0. If you find the zeros for this one, you end up getting 0 and 0, which is, you know, kind of pointless. So when we pretend this equals 0 with this one, what we're going to do is solve for y. So 3x would equal y, and that'll make that a little bit easier as far as graphing goes. I just moved the y over, and that's exactly what we're going to graph there, is going to be 3x equals y. And then we've got x greater than or equal to 0, y greater than or equal to 0. That is good news. That just tells us we're in the first quadrant. So now what we would want to do is figure out what to label our axes with. And we can see that we have to go out 90 in each direction. I know I have a 20 by 20 grid here, so what I would probably do is just take every 2 and make it 10. All right. So now if I go back and grab my green graph, that was at 90, 0, and 0, 90. Did have an equals bar, so that's going to be solid. And then I remember that it said x plus y has to be less than or equal to 90. And if I test the point 0, 0 in that, obviously 0 plus 0 is less than or equal to 90. But I'm also keeping in mind that this is just a first quadrant graph, and that's because of the bottom 2 down here. And then the other one that I needed to graph was my 3x equals y. Now, pretty obviously, that one's going to go through 0, 0. And I could either find a point on here that I could aim at, or I could certainly use the slope of up 3 and over 1. Because I had to go 90 by 90, I'm probably just going to put something in there and see what I get. So if I put 50 in for x, I'm going to get 150. So that's too far up. So I back up a little bit and say, okay, what if I put 20 in there? If I put 20 in this graph, that'll give me 60. I can definitely graph 20, 60, and aim for that. Now, that one was 3x minus y is greater than or equal to 0. I can't test 0 and 0, but it looks like 0.50 would be a good point for me to try, because if that's included, then I know I'm going to shade the kind of slender triangle upward and to the left. If it's not, then it's going to be the larger triangle that we see to the right hand, where the base is actually the x-axis for that triangle. So if I put 0.50 in there, it's going to say 0 minus 50 is greater than or equal to 0. No, negative 50 is not greater than or equal to 0, so we would shade in this direction. And obviously, given that we are staying in the first quadrant, this is going to be our feasible region. So now what we have to do is figure out the coordinates of our vertices there, and 0, 0 is a definite. And then we know that our green one was another one, so that's going to be 90, 0. Oops, missed a 0 there. And then we have to figure out the last one. And so for that, because this was on the calculator portion, you might just want to pop that one in. You know, we can say y equals negative x plus 90 up here for the green graph. And then we already have the red one solved. So if we put that into the calculator, we can definitely use second trace intersection and figure out what we have. So once again, we would have y equals negative x plus 90, or 90 minus x, it doesn't make any difference. And then we have 3x. And one of the things you probably want to do is make your window the same as what we were doing here, which would be 0 to 100 for both the x and the y. Intervals of 1 are just fine. Graph. So there's our x plus y equals 90, and there's our y equals 3x. Second trace. Number 5, let's get Blinky working here. The closer we can get to the intersection, the less work Blinky has to do. So you wouldn't have to do this. You could just hit enter 3 times, but it does go a little bit faster when Blinky is closer to that intersection. So we get a 22.5, 67.5. $22.5, 67.5. Now what do we do with that? We are going to put it into our objective function, f. And that objective function over here was 10x plus 11y. Well, 0, 0 pretty obviously is going to give us 0. 90, 0, 90 times 10 is 900. But we'd have to punch in 10 times 22.5 is 225 plus 11 times 67.5. And for number 32, that comes out to be 967.5. So the smallest number that we just had for an output there was 0, and that occurs at 0, 0. And our maximum of 96.75 would occur at 22.5, 67.5. And that's how we should write our answer for this one. So the minimum of 0, 0, the minimum of a 0 occurs at 0, 0. The maximum of 967.5 occurs at 22.5, the ordered pair 22.5, 67.5. All right, number 34, we've got red going for 3x plus 4y is greater than or equal to 60. That's going to have the zeros of 0, 15 and 20, 0. The green, x plus 8y, well, we want to pretend it says equals 40 when we're finding that boundary line. So that'll be 0, 5 and 40, 0. And this one that's a little obnoxious, 11x plus 28y equals 380. That'll be 0, 95 sevenths, but for graphing purposes, we want to think of that in its decimalized form, 13.571. And then 380 over 11, 0, decimalized form, 34.545. And then, of course, we have our x is greater than or equal to 0, y is greater than or equal to 0, which is great because that keeps us in quadrant 1. I'm just looking at this list, and good gravy, did you give me quite a few of these. All right, so got to be able to see largest number here, 34.545. So we could stretch this out a little bit if we wanted to. Oh, nope, we've got a 40 on there too. So we could stretch this out. I think I'm going to do that. Maybe go 4 blocks for each 10. like so. All right, we've got 0, 15, 20, 0. And if we test the point 0, 0 in that little bugger, 0 plus 0 is not greater than or equal to 60. So that means we are shading outward into the great unknown. The green one, we have 0, 5 and 40, 0. Notice the intersection there. That one again, if I put 0, 0 in there, 0 plus 0 is not greater than or equal to 40. So this one is shading up. Again, when I'm paying attention when I'm graphing this is where I have that double shading. And then our obnoxious 0, 13.571, maybe about there or so, and 34.545. Solid lines, all of these had equals bars. And 0 and 0 are less than or equal to 380. So I'm not going to shade, well, okay, I will. I'll shade there, but we can see the red and the green and the blue are here. So what that means is we have to figure out the coordinates for these three spots. And this one definitely was on the calculator portion, so you can do that. You can go back to the originals and solve them for y. All right, so we are solving our red and our green and our blue for y here. So we had 3x plus 4y equals 60. 4y equals negative x plus 60. So y equals negative 1/4 x plus 15. X plus 8y equals 40. 8y equals negative x plus 40. So y equals negative 1/8 x plus 5. Blue, 11x plus 28y equals 380. So we would go ahead and move the x over and divide by 28. And I wouldn't even bother reducing the 380 over 28. As long as you put that in with parentheses, calculator will be just fine with it. Now, I already graphed them on here because this has just been incredibly difficult graphing today. It's not taking anything that I'm punching in, so I'm doing it at the computer. And there it is. And there's the graph. So now, again, the colors don't match. You know, you could make it do that, but the point is we need those intersections. So second trace, oops, not number 5, it's number 5. Stop. Second trace, there we go. Number 5. And Blinky is way down here. So might as well go after that intersection first. Enter, enter, guess. There it is. Very nice. 1630, like that. Second trace, so you write that down, and then you go after the others. So I'm going to get Blinky up here by the intersection with the black graph, which was actually, for ours, the blue. Oh, now look at that. It went black and red. Well, we're going to have to make it jump a little bit. Let's go back. Second trace, number 5. All right, so here's what happened. It kind of defaulted back to the red. I'm going to make sure that Blinky is on the upper portion there, that blue graph, and press enter. And now that I see that Blinky doesn't know which one to use, he went to the red, I'm going to hit the up arrow twice, and that makes it go to the black. You see how it kind of went in order? It did red, blue, then black. So enter, enter through guess. And there's a second intersection of 412. And now let's move on down the black line here. Whoa, Blinky's in space. Second trace, number 5. And we are done with the blue one, so we need to hit the up arrow and then work our way down. Blinky catch up here. There we go. Just about there. Come on, Blinky. All right, so Blinky's in the area of that intersection. And now the second one, I want to make sure Blinky has grabbed onto the red graph. It's not looking good. Look at how he's in blue here. So I'm going to up arrow until I get red. Enter, enter. So that one's at 32.1. So yeah, definitely have to up arrow a little bit to get Blinky where he needs to go on this one. And so vertices at 16.3, 412, and 32.1. Now you go grab your objective function. And you put these little buggers into that objective function. This gives us 315, this gives us 360, and this gives us 505. So the minimum of 315 occurs at the ordered pair 16.3. The maximum of 505 occurs at 32.1. Again, no labels here. This one was, just basic. Here's your constraints. Here's your objective function. So Blinky got a workout there, but Blinky's going to get even more of a workout with some of the other ones you asked me about. And number 37 here, this one is already done. Go watch the 7-5 day 2 video and you'll get that one. 38, Paul's diet is to contain at least 24 units of carbohydrates and 16 units of protein. Food substance A costs $1.40 per unit, and each unit contains 3 units of carbohydrates and 4 units of protein. Food substance B costs 90 cents per unit, and each unit contains 2 units of carbohydrates and 1 unit of protein. How many units of each food substance should be purchased in order to minimize cost? And what is the minimum cost? All right, so our objective function is about cost. Well, they said up there that for substance A, it's going to be $1.40. So right now I have just figured out that for my X, I need to use the number of food substance A. So that means Y is going to be the number of food substance B that I have to use. So $1.40 X plus, and it was 90 cents per unit for food substance B. Now I'm going to go back and find those totals. It says it has to contain at least 24 units of carbohydrates. So we're going to have an equation about carbs, and it has to be greater than or equal to 24. Now let's go find the carb stuff. It says food substance A, 3 units of carbohydrates. Food substance B, 2 units of carbohydrates. So 3x plus 2y has to be greater than or equal to 24. I'm going to color code here. Now I need the other thing about protein because as I was reading through there, I noticed there's another total of protein. 16 units of protein, so greater than or equal to 16. Says food substance A contains 4 units of protein. Food substance B contains 1 unit of protein, like so. How many units of each food substance should be purchased in order to minimize cost? All right, well, you can only have a positive amount. So we're going to have X be greater than or equal to 0 and Y be greater than or equal to 0. All right, we need to figure out where to graph this stuff. So in the red, let's find our zeros. Carbs, 0.12 and 8.0. So there's our carbs. That's what we're going to graph for those. And then our protein, 0.16 and 4.0. And of course, we know we're going to be in first quadrant. So we get this on our graph. Now this one, if you're careful enough with your graphing, you might be able to find those vertices without having to use the graphing calculator, which would be pretty cool. If you use a ruler or whatever, you might be able to get them all on there. So let's see, the largest number we need to see here is 16. We're going to have to go by ones. We've got 20 grids here. Oops. Alrighty, so the green, we'll go with red. We'll do the carbs first. We had 0, 12, and 8, 0. Solid line, set at least, which of course 24 is at least 24. 0, 0, that's not going to work. 0 plus 0 is not greater than or equal to 24. So we're going out way into quadrant 1 there. And then our green was 0, 16 and 4, 0. Like I said, if you're careful at this point and you have a ruler, you might be able to get that one perfect. And that one was greater than or equal to also, so we're shading out this way. But what we notice is our vertices are going to be here, here, and here. And this one will not have a maximum because we can keep going forever out there into quadrant 1. But we definitely need to know what those vertices are as we work through this one. So pretty obviously 0, 16 was a good one. And so was our 8, 0. And unfortunately, the green and the red did not intersect at something perfect. You know, I was thinking for a second that maybe it was just my graphing. You know, maybe it's perfectly at 2, 9. But if you put 2, 9 back in there, you know, it doesn't work. It's not perfect. So that means GC time, which means we have to solve these for y. So red one, 2y equals negative 3x plus 24. Y equals negative 3 halves x plus 12. Green one, 4x plus y equals 16. So y equals negative 4x plus 16. And we're going to find where those little buggers are intersecting. So let me clear these out from our more complicated problem and put in our little negative 3 halves x plus 12 and negative 4x plus 16. Ooh, it didn't take the 6. I think I got to straighten out now. All right, so our window from the last one probably wouldn't be awful, but we went by ones on this one, so maybe we just do 0 to 20. We just want to know where that intersection is, so we need to let Blinky give us that info. So second trace. Come on, Blinky, catch up with me. There we go. Number 5. Blinky was not caught up. Second trace, number 5. There we go. And we're on the blue. Enter, red, enter, enter to guess. And there it is, 1.6, 9.6. So it wasn't perfect, but it wasn't horrible either. All right, those buggers need to go into our objective function, and our objective function was C equals $1.40x plus 90 cents y. So this is going to be about money when we get done here. And 0.16, put those numbers in for x and y and you get $14.40. 1.6, 9.6 is $10.88. And 80 is $11.20. And we can only find the minimum because this does not have a maximum. It keeps going forever. So our minimum right here at 10.88. Oh, I wrote them backwards. Let me fix real quick. 80 should be the 11.20. And 1.6, 9.6 is our 10.88. There we go. I wrote them in a different order on my paper when I worked through it. All right, so this is our minimum. The minimum of $10.88 occurs at 1.6, 9.6 for our little ordered pair there. Now in words, you'd probably want to say 1.6 of food substance A and 9.6 of food substance B. You know, something along those lines, just to pull it together in a sentence. Nice sentence at the end. Problem number 39 says producing gasoline. We have 2 oil refineries that produce 3 grades of gasoline. So right away that gets me thinking, if I only have 2 oil refineries, that's probably my X and Y, but I'd better keep reading here. And they're going to produce A, B, and C grades of gasoline. At each refinery, the 3 grades of gasoline are produced in a single operation in the following proportions. Refinery 1 produces 1 unit of A, 2 units of B, and 1 unit of C. Refinery 2 produces 1 unit of A, 4 units of B, and 4 units of C. For the production of one operation, Refinery 1 charges $300 and Refinery 2 charges $600. A customer needs 100 units of A, 320 units of B, and 200 units of C. How should the orders be placed if the customer is to minimize his cost? So, like it says here, we have the 2 refineries, and that's basically going to be our X's and our Y's. So, we will call Refinery 1 X and Refinery 2 Y. And I want to go for that objective function right away. And it says, how should the orders be placed if the customer is to minimize costs? So what I want to do is look for the information about the cost at the refinery. And it says Refinery 1 charges $300 and Refinery 2 charges $600. So I suppose we could use C for charge. 300X plus 600Y. Now we had a problem about paper that we covered in class that's very similar to this one. If you're wondering why so much for Refinery 2, well, chances are pretty good that that's the one that produces that high grade of gasoline. So now let's go back and find some totals and figure out how to represent those. And we're going to color code as we go through here to make sure that we know exactly what's going on. Well, we have 3 grades of gasoline, and that's A, B, and C. So I'll go after A first. And in Refinery 1, it produces 1 unit of A. And in Refinery B, where is it? Refinery B. Refinery 2 produces 1 unit of A. And then we have to figure out, well, how much did they need of that? So a customer needs 100 units of A. So we have to produce at least 100 units of A. I'm going to switch colors and go after B. So Refinery 1 produces 2 units of B. Refinery 2, where is that at, produces 4 units of B. And the customer wants 320 units of B. So we could produce exactly 320, but we could also produce more than that and hope another customer will come along that will buy that from us. Now I'm going to change the color again and go after the C. So let's see, I might have to scroll up here a little bit to get the information. There it is. So Refinery 1 produces 1 unit of C, and Refinery 2 produces 4 units of C. And that one, the customer wants 200 units of C. So again, we could produce exactly 200, or we could produce, you know, a little more and hope that somebody else will come along to purchase that from us. So what we absolutely know is you cannot produce a negative amount of gasoline. So let me get the extend page to work here. There we go. And that means our 2 other constraints, which are fairly natural constraints when you talk about word problems, because we don't have a lot of things in nature or things that are produced in the real world at negative amounts. That doesn't make much sense. So something like temperature can be negative, but that's generally not a constraint for many things. It could be plastic manufacturing plant, things like that. So anyway, we have our objective function. We have our constraints all set up. Next to go would be to graph it. And so we'll use the intercepts and think, well, okay, it's just x plus y equals 100. So if I put a 0 in for either one of those, I'm going to need a 100 in for the other. A little more complicated for my green B equation here. Got a little bit of math to do, and we think, okay, well, if we don't do any of the x's at all, 4 times 80 would give us 320. And if we don't do any of the y's, the refinery 2 here, we're going to need 160 to get 160 times 2 to be 20. And then the last one, put a 0 in for x, and it'll say 4y equals 200. That's going to be 4 times 50. And then put a 0 in for y, and we're going to need a 200. Now, the whole reason we do those is so we can get an idea of what we should use for intervals when we're graphing this. And we are in quadrant 1 because we had x greater than or equal to 0 and y greater than or equal to 0, our two refineries. So I'm looking at my y-axis. I see I have a 0, 100, a 0, 80, and a 0, 50. And I know I have 20 little spots for this. So, you know, we could go by 5s with this one and we would be okay. But I don't think I'm going to mark every 5, just so this doesn't become a big eyesore with all kinds of numbers running over the top of other numbers. And then I need to look at my x's, and I see that I have a 200 0 there. So that one will have to go by 10s. And again, I'm not going to mark them all. So it doesn't appear all cluttered. But it's always a good idea to get those intercepts so that you know what's going to go on with this. Now, I could get lucky and I could graph these, you know, using a ruler, and maybe I'll see exactly where the intersections are. So I think I'm going to cheat a little bit and use the straight line drawer. The problem with that is I'll have to color code myself afterwards because these are pretty thick. If I go after the red that you see up here, that's a really thick line, and I don't necessarily want that thickness. So I'll just go with this segment piece right here, and then I'll draw over the top of it. From 0, 100 to 100, 0 was red color coded. And my green, 0, 80 and 160, 0. And that one was my green. Now, before I get too carried away with this, I'm going to stop and do my shading. With all of these, because it's greater than or equal to, we're going to want to shade up. I should actually make that green there. There we go. And then my red shading would be all of this. And now we're going to add the blue. 0, 50, 200, 0. And that one is also shading outwards because we said we could produce too much. We don't want to produce too little. We have to be able to meet the needs of our customer, or they're going to go somewhere else. So now what we have to do is make sure that we meet red, green, and blue, and overemphasize that. And start to notice where those vertices would be. And those vertices would be in those 4 positions right there. Now, like I said, I mean, if I graphed this perfectly, well, maybe I just got lucky and maybe one of the vertices here is 40, 60. Now, if I want to see if that's the case, I better check 40, 60 in the red and green equations and make sure that 40 and 60, in fact, does work in both of those equations. Turns out it does. But let's just say for the sake of an argument that you've just got a scratch piece of paper and you didn't necessarily get this graphed really good looking like this one up here appears to be, because the other intersection that I see here that would be a, hey, you've got to find this, looks to be 120 and 20. And again, if I'm thinking that's what it is, I could put it in there and check. But let's go ahead and get these in the graphing calculator by solving them for y. So my nice little red equation up there, which is currently x plus y equals 100 because we want the boundary line, would be y equals negative x plus 100. And then my little b is 2x plus 4y equals 320. So we would subtract the 2x and divide by 4. So negative 1/2 x plus 80. And blue, I might have to fit over here somewhere. So that one we have x plus 4y equals 200. So we'll have 4y equals negative x plus 200, and we'll divide by 4 and get negative 1/4 x plus 50. So we're going to put those into the graphing calculator and find the intersections just to make sure that we have them right. I'm going to pause this at this point so that I can get the Smartboard calculator up and running. All right, as you can see, I have our 3 boundary lines listed here. And then in the window, I have reset this so it matches our x's and our y's on the by hand sketch. And I'll hit graph. And we're interested in this intersection right here. We want to know what that one is. And we also want to know what that one is. So second trace, number 5. And I've got to get Blinky out of here where I can see where Blinky's going. There's Blinky. So I might as well go after the red and green intersection first, but this this is very clunky. So you'll have to give me a few seconds here to, doesn't matter how many times I hit the mouse, it seems to only move once. It goes a lot faster with your hand calculators. Come on. All the way up there. All right, good. So now when I hit enter, Blinky should, yep, go right to the green line because that's the other one I wanted. If he doesn't, then I have to pop him up or down with the up or down buttons. And enter guess 3 times. There it is, 40, 60. So that would be the first one that we would write down. Now again, we already know this one. We graphed that point. We know where that's at, and we know this one. So the other one, besides the ordered pair 40, 60, that we're going to need is this one. So that's going to be second trace again, number 5 again, and maybe the right arrow works a little better. No, it doesn't. All right, so I'm going to pop that to the blue line. Hey, this arrow button's letting me hold it down. That is good. All right, so that's the intersection I want. Enter. And I want to see where Blinky is. What line is Blinky on right now? Oh my goodness, what's Blinky doing way down there in the negative y's? Yeah, Blinky grabbed onto the red one. We want the green. So I'm going to pop Blinky up. There we go. All right, Blinky, you're all confused. I want this intersection over here. Enter, enter. 120, 20. So we have our intersections. And like I said, these two we'll just read right off the graph. But what we needed were the 2 that we just found by using the intersections. So let's write those down and see what we can do. This is truly just an interesting problem here because if you look at these vertices, there's actually 2 of these we could cancel off right now. And that's because x and y both had to be greater than or equal to 0, it doesn't make a lot of sense that they're going to have 0 at one refinery and 100 at the other. But you know what? We can go ahead and put them in and see what happens anyway. And what we're doing is we're putting these values into that objective function from up above. So C equals 300x plus 600. If we put 0, 100 in there, we're going to get 60,000. If we put 40, 60 in, we get 48,000. If we put 100 and the ordered pair 120 and 20 in there, we get 48,000. And if we put the ordered pair 200, 0 in there, we get 60,000. So we have a tie because what this problem wanted, let's go all the way back up, since it was about cost. You know, you can think back, it's got to be minimized cost. How should the orders be placed if the customer is to minimize his cost? So we've got a tie here. And in fact, it turns out that we actually can use any x's there between 40 and 120. This one is kind of like a feasible region that shows up here. So any x such that x is between and including our 40 and our 120 will minimize costs at $48,000. And that's because those are our two middle grounds up here, you know, our 40-60 and our 120-20. And anything in between those two, it's on a line. So there isn't a spot that's below any other points. There aren't any points below any other points for this stretch, which means there's no possibility that it's ever going to be less than that. It's on a line. It's always going to come out to the 48,000 when we add those together. So kind of a little different. Wouldn't expect something to something with that little, you know, tweak in it to show up on your test, but we need to know that it is available and that this would give them some room for making decisions because they can produce it anywhere between 40 and 120 for the x's. Next one. Whew, finally out of those. All right, 40 says solve the system of equations graphically, and the instructions were don't bother with the corner points, just get them graphed. So we have y equals x minus 1.5. I'm going to make that red here. And so using y equals mx plus b, that means we need to go down 1.5. And from there, our m, our slope, would be 1 over 1. That looks like a negative. All right, so we carefully 1 and 1, 1 and 1, give ourselves a little bit to aim at, and graph our line. And then we have this luscious parabola here, and I can't stand decimals. So y equals 1/2 x squared minus 3. You might want to just make really a little quick table here. If you wanted to, you could use the transformation of moving down 3, so you wouldn't have to have a 3-part table, but this will be 1/2 x squared minus 3. We know these are symmetric, so we could probably just pick a few points to throw in here and square them and take times 1/2. Well, that's going to be 0. 1 squared is 1 times 1/2 is 1/2. 2 squared is 4 times 1/2 is 2. 4 squared is 16 times 1/2 is 8. And now what we want to do is just subtract 3 from those middle values there because we want the x's and the y's to show that transformation, which means it'll show that moving down 3. The other way to do it would just be graph 1/2 x squared and then physically count 3 units down. But I think this will be a faster way to get that. So we need to subtract 3, I'm blabbing too much. We're not going to graph those. You know, we just want to know what that final answer is. So 0, -3, that final transformation. And then we have 1, -2.5. And then we have 2, -1. And we have 4, 5. And symmetry will give us some other points to aim for. Now, these did not say greater than or equal to, less than or equal to, so we did not have to shade. With this graph, you know, what I would probably do is I would solve this algebraically. I mean, if we want to know what those 2 points are, I would say, hey, they both equal y, so they have to equal each other. All right, so move everything over to one side. Pretty obviously, this is a quadratic here. And multiply by 2. Makes it really nice. And what we're going to figure out here is where are the zeros. So that means we're going to go ahead and factor this. We'd have a -3 plus 1, which means x is 3 or -1. And then what we do is just take those and plug them back into either of the originals, and that will give us the coordinates where these two are equal to each other. So I like this one. If you take 3 and you subtract 1.5, you're going to get 1.5. If we put a -1 in there, -1 minus 1.5 is -2.5. So if we look at our graph, we should see that it looks like at 3, 1.5, these two are, and obviously I wasn't, you know, making this exact when we went through it. And then -1, -2.5. So going to be a little off graphically, but we've got it. And we didn't even have to do that part. All right, number 61, solve the system of inequalities. The top one is linear, so x minus 3y will be less than -6. Let's make it look like a line. And then what we want to do is find the zeros, since now it's in standard form, or you could put it into y equals mx plus b. That's totally up to you. But if we put 0 in there, we're going to need a 2 to get -6. And if we put a 0 in y, we're going to need a -6 for that one. So 0, 2, just going by ones here. And -6, 0. And this is dashed. It did not have an equals bar. And then I test 0, 0 in there. Is 0 minus 0 plus 6 less than 0? The answer is no. So we'd be shading out. Y is greater than x squared minus 6x plus 7. I would really like to have that one in vertex form, and that means I'm going to complete the square. So I'm going to subtract 7 from both sides, and then come up with that number that when I add it to both sides will make a perfect square trinomial. So y minus 7 greater than x squared minus 6x. We need b over 2. -6 divided by 2 will be -3, and when you square it, it is 9. So we're going to need to add 9 to both sides. That will give us y plus 2 is greater than x minus 3, the quantity squared from that perfect square trinomial, and then we're going to subtract 2. So we have y is greater than x minus 3, the quantity squared minus 2. That means our vertex with our x minus h plus k is at 3, -2. So there's our vertex. And then you could just go ahead and throw a couple more points in y equals x squared minus 6x plus 7 if you want to, so that you can see exactly where to have this shooting at. I'll put a 1 in there. 1 squared is 1. 6 times 1 is 6. 1 minus 6 is -5. Plus 7 is 2. 1, 2. Because of symmetry, we could go equal but opposite on the other side of the vertex. Maybe put a 0 in there. 0 minus 0 plus 7 is 7. So 0, 1, 2, 3, 4, 5, 6, 7. Symmetry on the other side. Now, be careful. That one did not have an equals bar either. Now, we can't use 0. Well, we could use 0, 0 to test it. I generally like to pick stuff that's inside the parabola to test, but you know what? Let's try it. It's either inside or outside. So we put 0, 0 in here. It'll say 0 is greater than 0 minus 0 plus 7. Unless they changed math overnight, that ain't going to work. So we're inside the parabola. And that means this is the region that would have the double shading. So be careful with that, with the dashed piece going on there. Oh, and again, said don't find the corner points or the intersections. What we wanted there was to see by shading, by graphing. That's how we solve these, to show all the solutions. So 52, partial fraction decomposition in the rational function all comes from factoring that denominator. So if we have x cubed plus 2x squared plus 4x plus 8, we're going to factor by grouping. And I notice an x squared will come out of both of those. So that'll be x squared times x plus 2, and a 4 will come out of the back. Obviously, x plus 2 is a factor, as is x squared plus 4. And x squared plus 4 is not factorable. That makes it an irreducible quadratic. That means that's going to have a linear factor to it. So a over x plus 2 plus bx plus c, there's our linear, over x squared plus 4 has to make this work. So let's see what we need to do here. We would have to take the first fraction times x squared plus 4 to make it work. And the second one, bx plus c times x plus 2 to make that work. Ax squared plus 4a plus, do a little FOIL, it's obnoxious FOIL, but it's FOIL, bx squared plus 2bx plus cx plus 2c. Now, go back up and see what we're supposed to get here. Our x squareds are supposed to come out to negative 1x squareds. Our x, negative 5x. And then we need 2 for our constants. So ax squared plus bx squared is supposed to equal a negative 1x squared. Then we have 2bx plus cx, and that's supposed to come out to be negative 5x. And then we have 4a plus 2c, and that's supposed to come out to be 2. So this would make a nice matrix that you could just do reduced row echelon form on. We've got 1a, 1b, 0c to give us negative 1. Then we have 0 a's, 2 b's, 1 c to give us a negative 5. And then we have 4 a's, 0 b's, 2 c's to give us a 2. So you could plop that one into the calculator and do reduced row echelon form. I'm going to stop this and put that in. You can see I have our lovely matrix in there. So let's go back to the main screen. And we need second matrix, math, alpha B, reduced row echelon form of second matrix number 1. So that's what we should be writing down. We should be writing down that 1, 0, 0, 1, 0, 1, 0, negative 2, 0, 0, 1, negative 1, because those are our answers for A, B, and C. So what this is telling us is A, B, and C, and the values we should use for them. So A is supposed to be a 1. B is supposed to be a negative 2. And C is supposed to be a negative 1. So we go back to figure out, okay, which one of these did we have over what? And A needed to be over the x plus 2 term, Bx and C over the x squared plus 4 term. Let's go put them where they're supposed to go. So we would have 1 over x plus 2 plus negative 2x minus 1 over x squared plus 4. And that's where we would have you leave it. I mean, that's very obvious to us that you knew what A, B, and C were. The book went ahead and said, let's pull a negative out of this one and put it in front. But you know what? They didn't do that at all when we went through the sections before. So we just want to have you stop right there. That would be great, because then we'll be able to see what your A, B, and C values were. Oh my goodness, that's almost an hour of video, but that covers all the questions you asked for.